How can a computer decide whether an email is spam? How can it recognize a handwritten digit? Or tell whether a picture contains a cat or a dog? Modern AI systems can perform incredible tasks, but at their core, they are built from a surprisingly simple idea, an artificial neuron. Today, we're going to build the simplest artificial neuron ever created, the perceptron. By the end of this video, you'll understand how it takes information, processes it, and makes a simple decision. The perceptron is one of the earliest artificial neural network models. It was introduced in 1957 by psychologist Frank Rosenblatt and became one of the first algorithms capable of learning from data. Although today's neural networks are far more powerful, they are still built on the same fundamental concept introduced by the perceptron. Let's take a look at what a perceptron looks like. At first glance, it looks very simple. On the left, we have three inputs, x, x2, and x3. Each input is connected to the neuron through a weight, labeled W, W2, and W3. The neuron also has one additional value called the bias, usually written as B. Finally, after processing everything, the neuron produces a single output. So before we can understand how the perceptron makes a prediction, we first need to understand the role of each of these components. What exactly is an input? Why does every input have a weight? And what is the purpose of the bias? Let's answer those questions one by one. Inputs. Now that we've seen the structure of a perceptron, let's understand what each part does. We'll start with the inputs. Inputs are simply the information that the neuron receives. They are usually represented as x, x2, x3, and so on. For example, imagine we want our perceptron to decide whether a fruit is an apple. The inputs could be x, how red the fruit is. x2, how round it is. x3, how sweet it is. These values are just numbers. The perceptron doesn't know what red or sweet means. It only receives numerical values that describe the fruit. Weights. Next, each input is connected to the neuron through a weight, usually written as W, W2, W3. A weight tells the perceptron how important an input is when making a decision. If a weight is large and positive, that input strongly supports the prediction. If the weight is close to zero, that input has very little influence. And if the weight is negative, that input actually argues against the prediction. In other words, weights allow the perceptron to decide which pieces of information matter the most. Bias. The last component is the bias, represented by B. You can think of the bias as the neuron's starting point before it considers any inputs. Imagine you're taking an exam that requires at least 10 points to pass. That passing score acts like a threshold. The bias adjusts this threshold. It can make the neuron easier or harder to activate. Without a bias, the perceptron would be much less flexible and would struggle to learn many types of patterns. How the perceptron makes a prediction. Now let's put everything together. First, the perceptron multiplies each input by its corresponding weight. So x is multiplied by W, x2 by W2, and x3 by W3. Then it adds all of these values together and finally adds the bias. The result is a single number called z, often referred to as the weighted sum. So at this point, the perceptron has gathered all the evidence into one number. But it still hasn't made a decision. That's where the activation function comes in. The activation function. An activation function is a mathematical function that takes the neuron's weighted sum, z, and determines the neuron's final output. For the original perceptron, the activation function is the step function. The step function is very simple. If z is greater than or equal to 0, the neuron outputs 1. If z is less than 0, the neuron outputs 0. You can think of it as a simple yes or no decision. Has the neuron gathered enough evidence? If yes, it outputs 1. Otherwise, it outputs 0. So the complete process looks like this. Receive the inputs. Multiply each input by its weight. Add all the results together with the bias to produce C. Pass C through the step function. Produce the final prediction, 0 or 1. This is the complete workflow of a perceptron. Even though modern neural networks are much more complex, every artificial neuron still follows this same fundamental idea: receive information, combine it, apply an activation function, and produce an output. Today, we've learned how a single perceptron works. It receives inputs, assigns them different levels of importance using weights, adjusts its decision with a bias, and finally uses an activation function to produce an output. While a single perceptron can only make very simple decisions, it represents the fundamental building block of modern artificial intelligence. So what happens when we connect hundreds, thousands, or even millions of these artificial neurons together? We get a neural network. And when we stack many layers of these neurons, we create what is known as a deep neural network. In the next video, we'll see how connecting many perceptrons together creates a deep neural network. Then, we'll begin exploring how these networks learn from data by adjusting their parameters during training.